So now that we've talked about solving some systems of equations and the various things that can happen, I want to talk a bit more generally about these things and give you some definitions and some procedural things here. So here we have a system of m linear equations in n variables. So what does this mean? All right, first off, a linear equation just means that it has no higher powers of the variable. So something like the equation of a line or a plane would be linear, but the equation of, say, a cylinder or a paraboloid, that would be nonlinear. Right? So only first powers of the variables are allowed. Okay? Now the variables here, notice there's no like x, y, z, and that's because there might not be enough letters. So we tend to call our variables x1, x2, x3, and so on, right? Rather than x, y, z. And we do this for a few reasons. One, it makes indexing easy. And another is, like I said earlier, we might need more variables than there are letters in the English alphabet, or in the Latin alphabet. All right? These a's here, these are the coefficients of the system. So like these would be actual numbers, whereas the x's are variables. Likewise, the b's are actual numbers. The way you read these numbers here, the a's, the coefficients, this one, we're not going to read this as A11. We're going to read this as A11. Okay, the next one is A12. Next one would be A13, all the way to A1n. All right, and then likewise, this is A21, A22, A2n, AM1, AM2, AMN. All right, what the subscripts here on these A's mean? The first number tells you which equation it belongs to. The first, the second, the third, so on. The second number in the subscript tells you which variable it belongs to. Is it the coefficient of x1? Is it the coefficient of x2, x3, xn? Right? Which one is it? Okay, so that's just some notation. This is going to become very important as time goes on, so I recommend getting a bit used to that. Get used to using x1, x2, x3, x4, and so on as variables rather than like x, y, z or something like that. Right? So, now that we have that, what is a solution of this system? Okay? So, let's give you a definition here. A solution to the system is a set of numbers let's call it, I don't know, S1, S2, ... Sn, that solve all m equations. Right? So if we plug in S1 for x1, S2 for x2, and so on to Sn for xn here, if we plug them in for the x values, it should make every single equation true. So we want it to be a solution of all of the equations simultaneously. Right? So that's what a solution to a system of equations is. Now, if you think back, we had some systems of equations that had more than one solution. That's why here we say a solution and not the solution. Because there might be just one solution, there might be infinitely many, or there might be no solution. All right? And actually, if you think back to the examples that we had, you'll notice it's actually a fact, what we just said. There's three outcomes. So there is 3 possibilities for a system of linear equations. For a system of, I want to emphasize here, linear equations. Right? Or I guess this should say there are 3. Right, so there are exactly 3 possibilities. Only one of these will be true. So 1, there is one solution. Right? 2, there are infinitely many. Solutions. Right? And 3, there is no solution. Right? So those are the possibilities. If there is a solution, as in these 2, this is what we call a consistent system. Right? A system of equations is called consistent if there's a solution to it. Right? If there's no solution, this is what we call an inconsistent system. Right? Hopefully that makes sense there. All right. So, one other thing I want to point out, when we were solving those systems of equations in the earlier videos, there are certain operations that we were doing, right? We were multiplying equations by a number, we were combining equations. Another one we didn't do, but perhaps it makes sense, is in a system of equations, if we flip 2 equations, that's not going to change the solution, right? That's just reordering. So whenever we do something to a system of equations, like flip 2 rows, or flip 2 equations, or take an equation and multiply it by a number, or combine 2 equations and replace one of the original ones with that output. Whenever we do any of those 3 things, we get what's called an equivalent system. Right? So it's another system of equations, it's a different system, but it has the same solution. That's the important part. So, right. So, let me sum up here. I want to call these operations that produce equivalent systems. Right? Again, equivalent systems are 2 systems of equations that have the same solution. Right? So the first one is interchanging 2 equations. Right? The second one is multiplying an equation by, it should specifically be a non-zero constant. Right? And third is we're allowed to add a multiple of an equation. Let me make that actually look like the word an equation to another equation. Right? So like when we were doing those things like 2 times equation 1 plus equation 2, right? And then we replaced equation 2 with that. That's what this third one is. Right? So if we do any of these 3 things, it doesn't change the answer to our system of equations. Right? So using this process in general is what's called Gaussian elimination. Okay? So this is Gaussian elimination. Right? So in the next video, we'll do an example of this. We did an example earlier where we went all the way down to like a very, very solved system where we said x is this, y is this, z is this. Right? In the next video, we'll do another one where we don't go quite as far. So that was Gauss-Jordan elimination. We're going to stop short of that in the next video.